15, let's get back to it. Again, I want to be efficient with your time. So we just talked about the solid phase and how the particles, atoms in this case, but could be molecules, vibrate in place. Now let's talk about liquids. So properties of liquids are going to be that the particles are essentially as close as in the solid phase. Particles are essentially as close as in the solid phase. Randomly positioned. And moving. Okay. So our picture of a liquid phase, well, so liquids can, because the particles are moving, liquids can change shape. So I'm going to draw a liquid phase in some sort of container, and then the particles are going to be randomly positioned, but about as close as in the solid phase. And I'm drawing them so that they fill the bottom of this container, because they'll move around to fill the bottom of the container. And the exact number of circles doesn't matter. And again, we are talking as a circle is an argon atom. I'll put one more in there. Okay. And those are supposed to be randomly positioned, so there's no three-dimensional order. Now, let me see if I got my page on there. There we go. For this one, so liquids exist at higher temperatures than solids. Liquids exist at higher, capital T, for temperature than solids. So we know that average kinetic energy is proportional to temperature. If the temperature is higher, more kinetic energy. And so now, as far as kinetic energy for liquids, yes, the particles are vibrating. So we'll draw some vibration lines. And movement. And so my representation of movement, I'll make movement in green. Movement's going to be arrows. And the little arrow goes between the particles. So the particles are moving. And they don't all have to be moving the same direction. But just draw a couple arrows in there showing movement. But there's two key things about a liquid. One is the particles are about the same distance as the solid. And the particles can move. Okay. Are they vibrating faster than solids? Good question. So really no. I mean, so the first layer of the chemistry onion is that no, they're really not. They're vibrating about the same. Think of and there may be slight variations, but basically they're vibrating at about the same amount of vibrations, and the additional kinetic energy is added as the movement. Okay? Yeah, good question. When I say vibrations, do I mean shaking? Yes. So here's my two. So here's my example of a solid. They're vibrating, but they stay next to each other. For a liquid, they are vibrating about the same, but they can move. So they're vibrating and moving. Yeah, shaking is a good way of saying vibrating as well. That's the liquid phase. Now let's move on to the gas phase. For the gas phase, so first off, the particles are very far apart. And anytime in science or chemistry somebody says very far apart, your first question might be, how far? So let me give you at least a rough idea. And the idea is that they are 10 diameters apart. And that's an approximation, right? That we're just drawing pictures to give us an idea of what a gas is like. So if, and your picture should have them approximately 10 diameters apart and moving very fast. And if your question is, what is very fast? As a rough example, 100 meters per second. So M is going to be meters. S is going to be seconds, or second. So 100 meters per second. So now here's our picture then of a gas. First off, draw a box because the gas needs a container. Otherwise, the gas just keeps on going forever. And so we're going to put gases in containers. And let's see. So if that's, again, an argon atom, then, and you don't have to do it this precisely, but I have a ruler right here. If my argon atom is approximately, well, it's a little less, but let's say approximately 1 centimeter, that means that the next one, if it's going to be 10 diameters away, has to be 10 centimeters away. So there it is. And it's supposed to be the same size. But now if I go 10 more diameters down here, so, and that's as many gas particles as we have. That's how far they have to be apart in our picture of a gas. Now I'm going to add in the motion here. So this time motion still will be in red, at least the most. So these are what are called speed lines to give you the idea that this particle is moving very fast. This particular particle just happens to be bouncing off the walls, so or the wall. So when I write what this is, it's going to say speed lines, particle is bouncing off wall. And then just draw some speed lines for the other ones as well. They should be going in some sort of random directions too. And yes, gas particles are vibrating too. So we'll put in some vibrations. But if you're moving at 100 meters per second, that is the main kinetic energy. The vibrations are, since they're still about the same as for the solid, are just a small amount of the kinetic energy. Yes, they vibrate, but like in layers of the chemistry onion, nobody cares about the vibrations of a gas phase. They just care about the kinetic energy of the 100 meters per second. Question, how far apart are the particles in an oxygen tank? Is the closeness in the oxygen tank the reason why the tank is flammable? Good question. So if you have an oxygen tank, so the pressure inside that tank is much higher. So, and we'll talk about this when we talk about gases, but if you have an oxygen tank, what you've done is you've compressed those particles so they are much closer together. I would say they're close together. They're probably 3 or 4 times their diameters apart. And an oxygen molecule, by the way, so O2 gas, so has 2 atoms. So we might draw an O2 like that, 2 atoms together. Now the question as to why it's flammable. So oxygen is actually what is needed to make fire. It is not actually flammable itself. So meaning that if you put a spark to oxygen, nothing will happen. But if you have a fire already and you put oxygen on it, it will make that fire go much faster. So oxygen is what's called, so it is required to have a fire, but if you had pure oxygen and nothing else around, no fire would exist because oxygen is not like wood burns. Wood burns when there's also oxygen present. But if you had pure oxygen, so what oxygen is oxygen helps fires go faster. So if you had a cigarette or something that was burning and you opened that oxygen tank, then the flames would get much bigger. So I don't know if that answers your question. We do talk about burning and combustion quite a bit in this class. Yes, so I guess the one other thing I wanted to say about gases is that gas particles are randomly positioned. Gas particles are randomly positioned. And maybe that's obvious from this, but just to be clear, there is no order in the gas phase. Okay? All right. Gas particles are randomly positioned. So those are our 3 phases, and what you can see is as you go from solid to liquid to gas, you get more kinetic energy. And we're going to talk about that a little bit more here. Question, how do you turn a solid into a liquid and then a gas? So we're going to say you raise temperature, where T is temperature, capital T is temperature. You raise temperature, which increases the kinetic energy. Okay. And then what stops all substances from being gases? That's going to be intermolecular forces. And my abbreviation for intermolecular forces is capital IMF. And intermolecular forces of attraction between particles and particles here, by particles I mean atoms, molecules, or ions. Tend to keep particles in the solid phase. And our journey in this course, starting here and talking about phases, will largely end with intermolecular forces. And we will be able to look at a molecule and tell what kind of intermolecular forces it has and whether or not we would expect it to be a solid, liquid, or gas. And really, especially for those who are interested in biology or nursing or pre-med, so that's a really important aspect of why you're required to take this course. So temperature adds kinetic energy, which tends to turn things into gases. Intermolecular forces of attraction tend to keep particles in the solid phase. And the course will say, we'll learn a lot about these two trends throughout this course. Okay. Now let's talk a little bit about the periodic table. So I've got a periodic table right here, and I've also got a periodic table right here. This is the periodic table that I'm showing right now that is in the Blackboard site under syllabus and schedule. So, and this is the one that I expect you to use on homeworks and have handy and print it out for lecture as well, because it'll be very useful to have a periodic table. I've got this one right here so I can make some notes on it. And the notes are going to be the following. As far as the periodic table, we're going to need to know some nomenclature, some naming, and what types of materials there are. I'm going to ask you to draw a line from boron, B, at a diagonal, and then from PO at a diagonal as well. And we're going to do a step structure here, like so. Now, the elements to the right are called nonmetals. And the elements to the left are called metals. So here, left, metals. There we go. And the elements touching this line, and I'll write that up here. So what I'm going to write is elements touching the staircase line are called, and the word is right here, they're called metalloids. Okay? And they're called metalloids because they're sort of like metals and they're sort of like non-metals, depends on what kind of case you get them into. But the non-metal-metal distinction is a very important one in this course because metals will act and have different chemistry than non-metals. So the reason we're going over this nomenclature is to help you understand how molecules and how ionic compounds form and why there's differences. So Zn right here is a metal. K, which is potassium, is also a metal. Here's Au, which is the chemical symbol for gold. Gold, we're used to being a metal. Gold, silver, and copper, these are very common metals. But what I want to make sure you know is all the way over here, Cs, cesium, is a metal as well. Okay? So they're all metals. These two rows and aluminum are called the main group metals. So I'll put this in green as an indication, and I'll also write in green are the main group metals. So however you're going to designate them, feel free. In my third color, so I'm all of these and all of these. Well, let's say this. These ones right here are called the transition metals. These are also transition metals down here at the bottom, so it's okay if you've got red down here. These ones down here are more specifically called the inner transition metals. But as long as you know that they're all transition metals, you're going to be fine. Okay. And again, the reason we separate the main group metals from the transition metals is because it's going to help us understand their chemical reactivities later on. Any questions about that? Okay. All right, so that's a little bit of periodic table nomenclature. We have another periodic table here because we're going to do more. And on this page, what I'd like to talk about is some of the names of the columns. And just what a column is. A column on the periodic table, that says column. A column is a chemical group or family. With similar chemical reactivities. With similar chemical reactivities. And so what does that mean? If I look at lithium right here on the column all the way to the left, lithium, sodium, potassium, rubidium, cesium, all of these elements will react similarly. For example, as I'll tell you shortly, lithium forms a +1 ion, sodium forms a +1, potassium forms a +1, etc. Now, some of the columns have names, and this column right here, the one all the way to the left, which is also called group 1, group 1 is called the alkali metals. Alkali, that's A-L-K-A-L-I, metals. And from the previous slide, we know they're metals, but they have a specific name. And we won't have to know the names of all of the groups, but there are a couple of them that will be important to know. And that's why I'm giving you these now. Group 2 is the alkaline earth metals. So Mg, element 12, magnesium, is an alkaline earth metal. Okay. Now there are two other groups I want you to know. The group all the way to the right over here, those are the noble gases. And the group right next to that, which is group 17, those are called the halogens. The halogens. And so those are the only four groups that I need you to know. Like if I say, which halogen is blah, 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 you can say, okay, I go to this group, and now I have limited what my answers can be to just one of the halogens. Let's see what else. Oh, so the one other piece of nomenclature is that we have to define a period. And a period in the periodic table is a row. And it's called a period and it's called a periodic table because as you go across a row, the chemical reactivities vary periodically. but as long as you know that a period is a row. And so you'll notice that the periods over here are numbered. So period 1 starts with hydrogen, period 2, period 3. These are the period numbers. So we might as well note that. So I'm just going to write an arrow and period numbers. And that's because later on we do refer to these period numbers, so good to know. Is there a name for different charges? The numbers on top of the columns. So the numbers on top of the columns are just called the group numbers. And the numbers in parentheses are the ones that I've been using. And the 1A, the ones with the A's and B's are an older system that we still put on periodic tables, but I will never refer to them by the A's and B's. I will refer to them as group 1, group 2, group 3, etc. And is there a name for the different charges? We'll talk about that. But the short answer is group 1 will form +1 ions, and there's no name for it. It's just we have to remember that. Okay, and we'll talk more about that in a minute. All right. So that's, I think, all of our periodic table nomenclature. And now we can talk about the formulas of ions. So A says memorize ions from the nomenclature handout. Make nomenclature flashcards for exam 1. If the nomenclature handout, which I did ask you to print out, is available in the syllabus and schedule folder in Blackboard, right here it says Chemistry 1010 Miller nomenclature. There are a bunch of elements to memorize. There are some prefixes to memorize, some common molecular compounds, and what I'm talking about right now is on the back or page 2 of that, common ions and their charges. Okay, so let's talk about this for just a minute. So first off, you should memorize all of these. It will help you with the class. But now let me say something different, which is this is an online class. And you'll see in the homework that you have nomenclature questions to answer. But if I give you a nomenclature test or a nomenclature question on the exam, since you're at home, it's very difficult for me to tell whether you're just looking at the sheet at home and writing down the answers. So I would suggest to you that you will see the nomenclature, like this is one thing in my lecture notes that is left over from when we did face-to-face. And when we go back to face-to-face, you will have a nomenclature quiz and on nomenclature on the exam. But since we're 100% online, you will not have nomenclature on your exam. So I'm going to put this in parentheses, and I'm going to say that there will be no nomenclature on exams. In remote mode. And parentheses in general mean something that it's good for you to do, but that will not be on exams. So parentheses means good to know, but not on the exam. Like sometimes I'll have to talk about some things to help you understand what is on the exam, but it won't be on the exam itself. And again, good to know. So question, I always thought nomenclature is essential for the course. Yeah, I think it is. I just don't have a good way to test it. So I strongly encourage you to memorize all of those, all of that nomenclature, but the way, and it will help you in the course. Yes, it is essential. It's like if you were learning, if you wanted to go to France to speak French, you would need to know a certain base set of things just to be able to live in France. Yes, nomenclature is just like that. You need to know a basic set of nomenclature, and it only helps you do better in the course. but I'm a realist and I want you to know what's on the exam and what's not. So I'm going to be as transparent as I can about the exams. And I'm not going to put nomenclature on there. So yeah, no, I think it's very important. But anyway, hopefully that answered your question at least as well as we can right now. Now, things that will be helpful to memorize, you do need to memorize trends in the charges of monatomic ions. So I'm going to take this word apart for you. Monatomic is monoatomic. Mono means, of course, one. So one. Atomic means atom. So these are the trends in the charges of one atom ions. You can see just one atom in each of these examples that I've given. And so Cl minus, so has a -1 charge. S2 minus is a 2 minus charge, or -2. And it's at this point that I'll mention the fact that when you're talking about the charge of an ion, the chemistry nomenclature, or the chemistry, what's normally done, is that you refer to it, so if it's a 2 minus or a 3 minus, or a 2 plus or a 3 plus, that you put the number first and then minus or plus afterwards. That's the convention. That's what's normally done in chemistry. You don't have to do it like that. Like, I don't care. As long as you have the correct charge, you can refer to it as 2 minus, or you can refer to it as -2. But I will typically refer to them how it's done usually in chemistry. And that's what I've done down here. Typically list the number first. But again, you don't have to. And of course, if it's just minus or plus, there's no number to put. Sometimes I will put the number anyway, like 1 minus, or just because I want you to see it as part of your notes. But anyway. Yeah. Now let's talk about the trends. And to do that, we'll go to the next page. And we have another periodic table. Now, let's start with group 1. In group 1, all of the ions are, well, here, I'm going to do it. I'm going to put 1 plus ions, or you could just put plus. 1 plus ions. So you should memorize that if it's lithium, it's lithium plus. If it's sodium, Na, it's Na plus. So, and these are, the charges are superscripts, so they're raised up. But you can also continue down the row. All of these form +1 ions. Group 2, 2 plus ions. And I'll just give one example. And this time I'll do barium. And it's barium 2 plus, Ba 2 plus. And that's a superscript. Now let's go over to the other, skip over to the other side. The noble gases form no ions. And in fact, one reason they're called the noble gases is because they don't react at all, and they're noble. They're above the rest of the elements. So they don't react, they don't interact with any of the other ones, any of the other elements, have you say. So no ions. Then the halogens, and I'll put this up here so I have space for my another couple rows. The halogens form 1 minus ions. So for example, like we saw on the last page, Cl minus. Oxygen's group, group 16, forms 2 minus ions. O2 minus is an example of that. And nitrogen and phosphorus in group 15, those are the only non-metals if you go back to the metal sheet. You get into the metalloids and things get more complicated down here. So I am going to, and I'll do it in green. Nitrogen and phosphorus form 3 minus ions. And again, remember, these are just the monatomic, the one atom ions. But an example would be nitrogen 3 minus. And we'll get to what are called the polyatomic ions in a bit, but these are just trends in monoatomic ions. Now, what about the transition metals? And so, before I talk about that, these two columns, nothing to memorize. So column 13 and 14, nothing to memorize. Now let's talk about the transition metals. The transition metals, most of them form 2 ions. Not all of them, because that would be too easy, but most of them form 2 ions. And so the transition metals are really what you need to go to your nomenclature sheet. And if you go to the nomenclature sheet and you go to copper, you can see copper forms copper plus, and the name of that is copper 1 ion. And then if you go down to the plus 2s, you'll see copper forms copper 2 plus. Those are the ones that are really helpful to memorize. I'm going to write the copper example on our page. So we have copper plus, we have copper 2 plus, and whenever there's 2 choices, that is reflected in the name. And so copper plus is called the copper 1, where this is a capital Roman numeral, and it has parentheses around it. And this one's copper 2. And the thing to remember is, it is the charge that is the Roman numeral. The Roman numeral is the charge. It is not how many of them there are. The number of them in the compound will vary. Okay. And then as a counter example, and I'm sort of out of space up here, so I'm going to put it down here. There's silver. And remember I said most form 2 ions. Silver does not. Silver is just silver plus. And so it gets no Roman numeral in its name. If there's only one choice, you don't need a Roman numeral. And if you think of chemists as people who love to categorize things in a systematic way, then you'll think about this, because whenever there's a choice, we need one other part of the name of the ion. When there's no choice, you just have to memorize that one charge. And yeah. But again, there's no nomenclature on the exam. However, I strongly encourage you to work through this. You'll see that the homework becomes easier the more nomenclature you know. Any questions on that? All right. So now, that's as much nomenclature and theory as we're going to do right now. Let's get into some calculations. Let's talk. The first calculation we need to know is density. And density, let me go back to black. Density is represented by lowercase letter d. We've been going about 40 minutes again, so let's take a break. It's 9:54 right now. I need a little snack personally. So I won't be able to answer any questions right now, but I'm going to take about a 5-minute break, and I will start lecturing at 10 again. Please go stretch, have a snack, whatever you need. We'll go for another half hour starting at 10, or half hour to 40 minutes.